Hello and welcome back to Particleworks Power-Ups. Today's episode is inspired by a question from a yellow goods manufacturer using Particleworks to simulate piston cooling. They asked, "We're using your generic piston motion script, but there are so many variables to define in multiple places. Could you write a macro to streamline the setup?" Great idea. Let's take a look at the current setup in Particleworks and how we've improved it. At EngineSoft UK, we've created a fully parameterized piston motion script. You just need to define the crank center, the big end, the small end, and the angle of the liner relative to the horizontal. It works for all engine configurations, inline, V, W, but the setup process is still quite manual. First, you'll need to input the geometry-specific parameters into the common script. Then, for each component, you must set the correct center of rotation. After that, you apply the keyframes for both piston and rotation. Finally, we include a calculation for the maximum piston speed to help with the time step settings by creating an empty group and calling a function in the common script. For engines with multiple pistons, this quickly becomes repetitive and time consuming. So let's fix that. Let's automate it. Because this is a longer script, I won't walk through it writing it line by line. Instead, I'll guide you through the main steps in the macro and explain how it all works. We start with the standard initialization block. No extra libraries needed, but we do need the scenes project. The large script you see here is our common script, the one that handles all the motion calculations. You don't need to modify it manually, the macro will take care of that. I've added a comment marker with just the word break, which we'll use as a place to inject new component parameters. Step 1. Confirm before continuing. Because the macro will overwrite the common script, we first show a dialog box asking if the user wants to proceed. If they cancel or untick the confirmation box, the script exits. Step 2. Add the crankshaft and update the script. We open a second dialog box with inputs for horizontal and vertical axis, engine RPM, crankshaft geometry file path, center location, and optional material assignment. We also do some validation. If no file is selected, the macro will prompt again until one is provided. We then calculate the axis of rotation based on the inputs, converting from numeric form, i.e. 0 for x, 1 for y, and 2 for z. This is wrapped in a try-catch block to handle any errors if the axes are defined incorrectly. Once that's done, we update the common script by splitting out the break comment and inserting the new parameters. Next, we add the crankshaft model to the scene, assigning the geometry, name, color, center, and material. To apply keyframes, we create an animation object, set its type to script, and assign it to component by specifying the keyframe type, axis as a number, and the animation object. Again, all of this is inside a try-catch to catch any issues. Step 3. Add piston and rods. We initialize a Boolean variable to control the loop and a counter for piston numbers. A new dialog window asks for geometry file paths for the piston and rod, center locations, material assignments, liner angle, and whether the user wants to add another piston. As before, if any file is missing, the macro prompts again. Once the input is collected, we again update the common script by inserting new component-specific data after the break comment. We can then create the models in the scene and apply the relevant properties. Rotation keyframes are handled just like the crankshaft. For translational keyframes, we use a loop to apply the motion in all three directions, updating the axis in each pass. After that, we check whether the user wants to add another piston. If yes, the loop repeats and the piston counter increments each time. If not, we simply move on. Final step, add the maximum speed output. We create a new group and apply the script to its keyframes to calculate and output the maximum piston speed. Finally, we rename the group clearly and save the scene just in case. That's it. Let's save the macro and see it in action. I've started a new scene and loaded in the engine block so we can check motion visually. To run the macro, I drag and drop the Python file. First I get the confirmation prompt to ensure I don't accidentally overwrite anything. Clicking OK opens the crankshaft input dialog. I've entered values measured from CAD and choose the crankshaft file. Here's a tip. Move your geometry files into the scene folder to save you time navigating. If you haven't defined materials yet, just click the three dots next to the material input to open the Material Property Manager and create new ones. Clicking OK creates the crankshaft and opens the piston and rod input window. I populate it with the correct file paths and settings for my first piston and rod pair, making sure the Add Another option is ticked. I repeat the process for the second set, but this time I untick the option since I don't need to add any more. That's it. The full motion setup is now complete and working beautifully. To check the maximum piston speed, I just select the group that we created and look at the X value in transform location. If you want to change the engine speed, simply update the RPM value in the common script. This will automatically update the motion and the calculated maximum velocity. If you have a problem you'd like our help with, our contact details are on screen now and in the description below. For more information about our full API online training course, visit our contact page for details. See you next time.